Thank you, Alberto, for the introduction. And first of all, I would like to thank all organizers for putting in this nice workshop. First, I would like also to apologize because there was some overlap with another conference and I could not attend at the given time the talk this week, but I will next week. And so, yes, my apologies for that. But I'm really happy to be there, and it would have been a pleasure to be in India with all of you, but this will be for next time. So this program is about classical and quantum transport processes. And as you will see, okay, my talk is more about quantum transport and quantum dynamics, but we managed to do some nice analogies with classical system and classical dynamics. And in particular, you see this graph on this first slide showing some physics that you know very well about the damped harmonic oscillator. And in fact, so I will consider in this talk an open quantum system, very simple, a 2-qubit out of equilibrium system coupled to 2 bars, which can also be operated as a thermal machines. So Alexia discussed this topic a lot in her talk. But me, so I will more focus on the quantum dynamics. So let me start this talk, and all results that I will present now were recently published in PRX Quantum, and here is a complete reference. And also, please do not hesitate to ask questions during the talk. Okay, sorry, now I cannot. Wait, I'm just, I don't know why my arrows are not working. So excuse me, I stop sharing and I will share the PDF file, which might be a safer option. I'm sorry for that. That's a paper by Alexia that you can see. Okay, now it is. Sorry.
Ça suffit la pub.
I was curious about some details. So, okay, now it is. So first, let me acknowledge my collaborators. So this work was done with my PhD student Shisha Kandelval here in Geneva, and my colleague Nicolas Brunner, who you may know. And we are working also on follow-up on this project. And so let me mention a master student who is also very motivated in that topic, Soumya Kumar, working at the IAS Bhopal. So, okay, first, this work was introduced as was motivated by investigating the quantum dynamics of quantum thermal machines. So let me briefly remind, for those who are not so familiar, that in general, thermal machines can be seen as an open quantum system out of equilibrium, where you have a quantum system, a working fluid coupled to several reservoirs. The simplest setup is like a 2-terminal device where you have 2 reservoirs which can be biased in temperature or in voltage. And you want to exploit these resources to perform some task. And there are classical tasks we are very familiar with, producing work, cooling another system, rectifying heat current, for instance, or charge current, or producing quantum correlations. It's a very active field of research. There have been experiments exploiting quantum mechanical degrees of freedom, like energy quantization. Here it's a single dot heat engine. Or for instance, with my colleague Francesco Giasotto in Pisa, we were exploiting single particle quantum interferences in an Aharonov boomerang to propose a thermoelectric engine. And this last picture relates to a series of works we have been doing with my colleagues in Geneva, where we want to exploit thermal resources to create quantum correlations among the constituents of the quantum systems. And this was more the topics that I presented beginning of the week in the other workshop for those who also attended it. So these are just different examples. It's not at all an exhaustive list. It's just illustrating some current research directions. So main questions now is like, is there a quantum advantage of using a quantum mechanical system to perform some given task? What are the role of quantum fluctuations? Are there some many-body advantages? And one can also look at whether it could be like more advantageous to operate these out of equilibrium devices in the steady state regime or in the transient. So really looking at the time-dependent dynamics. So in this work in this talk, as you probably already understood, I will focus on the last question and show you that in the transient dynamics, there are some very interesting features. And yeah, so and this we know that there might be some interesting physics, no? Because if I now introduce the damped harmonic oscillator, so that's the position as a function of time that I show, you know that as a function of the damped, the friction versus the frequency of the system, the eigenfrequency, then you can reach different types of regime that will tell you how your physical system is reaching its steady state. And it can reach its steady state by undergoing oscillations. This is a so-called underdamped regime, or it can reach it in a longer time, that's the overdamped regime. But it can also, you can also tune your parameters to reach a very specific point in the parameter space for the damped harmonic oscillator, which is a critical regime. And critical regime or critical damping is exactly the point where you are at the limit between a non-oscillatory behavior and when you do not have any more oscillations in your dynamics and when you reach the steady state in the fastest way. So we know that there are some very nice physics there. And I will show you that, in fact, for quantum systems, we can also achieve these types of dynamics. So the outline is the following. I will first present you the tools we use to investigate and describe and analyze the full dynamics of a simple 2-qubit out of equilibrium system. I will show you that we can find certain types of mathematical points, which are these Liouvillion exceptional points, and of course I will define them. And I will show you that we can exploit them to control the dynamics, and we can reach critical damping. Okay. So for the quantum dynamics, so that's a bit more, that's a bit the formal or technical part, no? So I will quit this type of nice drawing and go to something more precise. You can consider a more general setup, but for the moment, I will just consider two-level systems with which are degenerating energies. That's why, and the energy here is denoted with this epsilon, and they are interacting with a coupling strength G. Here, so you can choose the types of interactions. Here in our model, we choose a flip-flop type interaction Hamiltonian, or X, which is the same as a XY Heisenberg type interaction Hamiltonian, and it's just an exchange between the computational state 0, 1 and 1, 0. And so you know that if in general, no, how do I describe the evolution of my quantum systems? I take the von Neumann equations and I can write this differential equation for the density operators of my system, which is simply rho dot is equal to minus I over h bar and the commutator of the Hamiltonian of the system and the density operator. And now, okay, what happens if I consider that system where, in fact, each qubit is also coupled to an environment. And here as environment, I will consider thermal bath, but okay, you could consider other things. And in general, the two are characterized by different chemical potentials or different temperatures. Here I consider different temperatures. And gamma 1 and gamma 2 are just the coupling strengths between the qubits and the bath. So you also have to specify now how the dynamics between system and bath takes place. Here we considered again a single particle tunneling between system and bath, which is of the same form as that interaction Hamiltonian. We made several assumptions to be able to derive an evolution equation for this open quantum system. And in particular, we were assuming a weak system-bath coupling and Born-Markov approximations, such that in this case, you know that you can, the dissipation is captured by this type of super operators, where it just describes so the non-unitary evolution, and these are jumps produced by the coupling to the environment. And because it's G is the coupling strength between the two qubits is weak, in this system, your bath, for instance, the red bath at temperature T1 will only see the left qubit, okay? So the action of the bath onto the left qubit is described by local jump operators, sigma plus and sigma minus, which are the equivalent of the raising and lowering operators that we know for bosons, but here these are for fermions, okay? They are just jumping in and jumping out operators. So we know that we can capture the dissipation with this super operator, and so this allows us to write a Lindblad-Master equation that you can formally derive from first from Bloch-Redfield equations, making the different approximation and using perturbation theory. So, but here I won't redo it, but it's not phenomenological. No, you can really rederive everything. And here, so you recognize the free evolution due to the Hamilton of the two qubits. And here are the dissipators. And just to explain you here the two terms, so the super operator applied to sigma plus and the other one to sigma minus, in fact, they simply capture the fact that an excitation or a quasi-particle can jump in from the bath to the system, and this will be described by the process plus, and the rate is the following. And when the system loses an excitation, no, it's described by sigma minus, and it comes with a rate. And this rate, gamma plus and gamma minus, they are given by the Baire rate, and they depend on the types of baths that you consider. So in particular, they will depend on the statistics, the quantum statistics of the bath. If you have bosons or fermions, you will consider the Bose-Einstein distribution or Fermi-Dirac distribution. And for plus and minus, the statistics tells you how these statistics, how the mean occupation number should enter. So, and this is so the Lindblad-Master equation. So now what you want to do, if you will be interested in the steady state regime, you will simply solve rho dot S is equal to 0, okay? But if you want the full dynamics, it's much more involved. Indeed, so you see, this is my Mejia-Monasterio equation is an evolution equation, a linear differential equation. And in fact, all this entire term here can be is also called a Liouvillion and denoted by this calligraphic L, where L is a super operator that is applied to my density operator, and it's non-Hermitian, of course, because of dissipation. Okay, HS is Hermitian, but the dissipative terms are non-Hermitian. And so, from this differential first order differential equation, I can write the general solution, where I just have to exponential the super operator. So writing this general solution is easy, but in fact, working out the solution is in general very complex. And it can be solved, for instance, if the super operator L is diagonalizable with some eigenvalues lambda I, because then the solution is simply given by that one, where the density operator of the qubit at time t will be given by a combination of these S matrices, which are the transformation matrices that you use to diagonalize your Liouvillion. And then, as you know, if my operator here is diagonal, I just have the eigenvalues entering the exponential, so I can write this solution. And of course, it depends on the initial state, as we know. So this is a formal solution. And so what I would like to emphasize here is that, you see, it is a spectrum of the Liouvillion. So what is a spectrum? This is a set of eigenvalues lambda I that will set the exact dynamics of your reduced quantum system, okay? And so in more details to explain this, this fact, let me so take the case of our model. So we have 2 qubits. So the density operator, just for the dimension, it's a 4x4 matrix, okay, in the computational basis. And the Liouvillion, it has, to write it as a matrix, this super operator, you have to vectorize your density operator. So in general, the Liouvillion has a dimension n squared if n is the dimension of your density operator. So here it is a 16 by 16 matrix. And so we could diagonalize it, okay? And here I show the eigenvalues of this operator for this specific model. I show you the eigenvalues in the complex plane. So real axis is the x-axis, imaginary is the y-axis. And what you see first is that one eigenvalue is 0, and this eigenvalue will correspond to the steady state. And the other ones, in fact, they tell you how your system will decay towards the steady state. Okay. So you can remark several things. First, that all the eigenvalues have a negative real part, and this is necessary to ensure that your system will converge towards its steady state. So, in general, so okay, maybe you can. If you're not very familiar with that, you can see that easily with this. You see the density operator at time t, so it's set by this matrix with the eigenvalues. And you see that if all eigenvalues here have a negative real part, all this term will decay to exponentially to 0, okay? And if there is one eigenvalue which is equal to 0, then you just have that rho s of t does not depend on time, and it's given by s minus 1 rho s. You do the matrix products, but this will correspond to the steady state. It's not always the case that your open quantum system has a unique steady state. There are some conditions to know whether your system has a unique steady state or not. Here in our case, it's we have a unique steady state. This is why we just have one single eigenvalue with a zero real part. Okay, and all the eigenvalues, they comes in complex conjugate pairs, and so the full dynamics here is just given by this sum over all exponential functions with the eigenvalues, some coefficients that depends on the initial state, and the eigenvectors corresponding to the eigenvalues of your Liouvillion. So here I remain very generous, but if the first eigenvalue is the one being zero, corresponding to the steady state, then my time evolution of my reduced density operator is given by the steady state plus a summation over different terms. And these different terms describe exactly the decay modes towards the steady state. So I hope this is clear now. These types of decomposition is not new. No, it was used, for instance, to describe metastability in transient dynamics, for instance, in the first paper here that I cite. And it was also put forward in the context of non-Hermitian physics by, in particular, these two papers by Fabrizio Miganti, who is now a postdoc at EPFL. So in the following, I will not consider the full Liouvillion subspace. It's a huge one, but in fact, because we have investigated this model before in previous works, we know a bit how it behaves, and we could simplify the analysis by focusing on the eigenvalues of the Liouvillion that will determine really how the decay modes that survives in the that leads to the steady state behave. Okay, and this is because we have a specific type of interaction Hamiltonian and so forth. So it's determined by the form of your unitary dynamics. So we'll focus only on the steady state subspace. And so now I will explain you a bit what we found in this subspace. So, in fact, the decay mode that remains in this in the steady state, are the ones that I highlighted in red. So there are 6 eigenvalues, λ1 for the steady state, and 5 other values. So my Liouvillion, you see now, has a reduced dimension. And my dynamics now, I just describe it with a sum over 6 terms. So what are these eigenvalues? Now I can enter a bit, I can be more precise. So the spectrum is the following. So we have one eigenvalue, which is non-degenerate, given by minus gamma, 2 eigenvalues which are degenerate, minus gamma over 2, and 2 other eigenvalues which depends on the coupling strengths between the 2 qubits for this G, as you can see. So just to not lose you, let me just tell you that this gamma and delta gamma, they depend on the coupling strengths to the base, gamma 1 and gamma 2, and the statistics. So here are the definition. Gamma is just the sum of big gamma 1 and big gamma 2. Delta gamma is the difference, average difference. And these big gamma are just the sum over the incoming and outgoing rates for each pass. Okay? And so for fermions, they reduce to the bare rates. For bosons, they are just given by that. But so what you have to remember is that these are really gamma and delta gamma depends on the bare coupling rates to the base and on the statistics in the case of bosons, so they will also depend on the temperature and energy of the qubit, okay? And G, the interqubit coupling strengths, only appear here under the square root. So now, if we just do math, we can play a bit with this spectrum, no? And what you can see is that if G takes a special value such that what is under the square root is equal to 0, then I will have lambda 5 and 6, which will be degenerate. Okay, so they will be the same, minus gamma over 2. And they will also be degenerate with lambda 3 and 4. So if I take a specific value of G such that this term is equal to 0, you see that something very specific happens to my spectrum, and so to the decay modes that tells me how my system is approaching its steady state. And this specific point where G takes this very specific value such that what is under the square root is equal to 0 is an exceptional point. So before explaining you what I wrote below, let me tell you that an exceptional point corresponds to a degeneracy in your Liouvillion spectrum. So this is what I explained before. But it's not only a degeneracy in the eigenvalues. And this you have to be careful. It's also the coalescence of the corresponding eigenvectors. So to reach an exceptional point, you must have at least 2 eigenvalues in your Liouvillion spectrums, which becomes degenerate, and also their corresponding eigenvectors, which coalesce. If the 2 eigenvalues are degenerate, but their eigenvectors do not coalesce, it's not an exceptional point, okay? So, as I told you before, if the square root is equal to 0, we have 4 eigenvalues which are degenerate, but in fact, only 3 of them have their eigenvectors which coalesce. And that's why here I wrote it's a third order exceptional points, because it's only lambda 4, lambda 5, and lambda 6 which coalesce and which have their eigenvectors coalescing. Okay, lambda 3 does not belong to this exceptional point. So I saw one question. Is there one question on that or on what I said?
Doesn't seem so.
Okay. So I continue. So we have in this system a third order exceptional points. So what happens is that at exceptional points, I have the merging of lambda 5 and lambda 6 to this central point, and my Liouvillion becomes highly degenerate. Of course, if it's degenerate, I do not, and the eigenvectors coalesce, I do not have any more complete basis for this matrix, for my operator. But there is a way to derive a generalized basis in this case, and this here I won't enter into too many details, but you can write the Jordan form of this matrix, and you can apply the Jordan chain to derive the generalized eigenvectors. So that I just want to tell you that we can work with this matrix at exceptional points. It's valid. And so now I can exponentiate this Jordan form to get my exact solution of my system, okay? This is the eigenvalue 0 corresponding to the steady state. Here I have lambda 2, lambda 3, nothing special. And here I have the Jordan form. And what you see is that on top of the exponential decay, I also have now polynomial dependence in time that will alter my dynamics. So dynamics clearly is expected to be modified, but how, and are there some specific signatures? So this is what I would like to tell you now. But before, I would like briefly to mention that okay, exceptional points, it's a topic that has attracted lots of interest in the past years, and it's quite nice because there have been numerous experiments with different platforms, which I mentioned here, and it is that in general, so these are, for instance, with optics and photonic systems. So people there, they take optical or photonic system with two modes. So it can be two harmonic oscillators or whatever. Here you see two pumps, each described by a mode. And in fact, the trick to reach these exceptional points is to engineer the gain and loss of these systems. That's the general idea behind. And if you can control gain and loss, you can reach the point in parameter space where you can have exceptional points, and maybe you have heard about it, PT symmetry, which can also be interesting for quantum sensing or this, for instance. So there are experiments with optics and photonics. There are several experiments also with NV centers, where they have you see evidence third order exceptional points, second order exceptional points. There are some topology properties of exceptional points. Here, just to show you some experiments. And there are also experiments with superconducting qubits, where again they engineer the loss and gain between different excited states, and they see that at some for some coupling J, you see here, well, it's orange, no, on the top of this figure, and suddenly you clearly see oscillations via the orange, black, white region, and so this is a phase transition between broken and unbroken phase. But just to tell you that, okay, there are interesting stuff happening at this point. But what is common in all these experiments, no, is that they require lots of engineering to control the loss and gain to achieve PT symmetry and reach an exceptional point. And in fact, with my colleagues in Geneva, we were asking quite different questions, namely whether it's possible to investigate this interesting physics with just out of equilibrium open quantum systems without engineering gain and loss. Okay, so can we just see these types of physics when we do not engineer gain and loss? And in this work, we show that it was possible, and moreover, that it exists so in this very simple 2-qubit system with realistic values for the different parameters. So this is really the main achievement of this work. And so now the question is, but okay, what are the signatures in this open quantum system? So in this open quantum system, as I told you from this matrix, okay, it's evident that the dynamics will be different because now we have additional time polynomial dependence. And we expect that this polynomial dependence will show up at short times, no? Because at long times, it's anyways the exponential decay that will take over. So indeed, here I show you, so I will introduce this measure a bit later, but just to tell you that if one would expect a purely exponential decay, one will get the dashed black line, okay? But if you choose certain initial states such that you're able to probe this polynomial dependence in time, then you get a clear deviation compared to this pure exponential decay. And this is illustrated by this green, blue, and red line. So at short times, this is just an illustration of the maths that are in this Jordan form. Then whether this can be evidenced in an experiment, honestly, I think it's quite hard, because you cannot see that with any initial state. It's quite complex, and the deviation is not super large. So I'm not sure that's a very useful signature, but this is just about the math of the dynamics. But now we found something a bit more exciting. And here, so I come back to the damped harmonic oscillator. So we have these three regimes, critical, overdamped, and underdamped. And we know that critical damping happens at gamma squared is equal to omega 0 squared. And it is when the system reaches a steady state in the fastest way without oscillations. Okay. In fact, this critical damping, this exact point in the parameter space, it is an exceptional point of the Liouvillion of the damped harmonic oscillator. So if you write the evolution equation of the coordinates x and p, okay, so x dot, p dot as a function of x and p, you get a 2x2 matrix. And this 2x2 matrix is a Liouvillion, so it describes the dynamics of your classical system. You look at the eigenvalues, and in fact, you will find an exceptional point. And these exceptional points exactly correspond to this point in parameter space. So the question is the following: is there something similar in our 2-qubit open quantum system? So what we want to see now is how our quantum system approaches its steady state. So we need a measure, a tool to assess how it approaches its steady state, and we used the trace distance. So the trace distance is defined. It's the norm 1 of my density operator minus the density operator at steady state. Okay, and formally it is given by this. And it tells me so how close I am to the steady state. So when my system is in the steady state, you see that this trace distance will take the value 0. So now I show you this trace distance as a function of time for the 2-qubit open quantum systems. And I have considered different initial states, because my transient dynamics, it depends on the initial state. So I took for the 2 qubits to be initially in a singlet state, so that's a maximally entangled state, the 2 qubits being in a ground state, or the 2 qubits being in a thermal state, in a product of thermal states corresponding to the temperature of the 2 baths. Okay. And now, for these 3 different states, I investigate my dynamics at exceptional points. So when I reach the specific value of G that should depend on the coupling to the bath. And so this was not at exceptional points. And at exceptional points, I show you the trace distance with the dashed curves. And let us look at them together. So we see that for the green curve, the dashed curve is below the solid curve, okay? But for the blue one, okay, it's not the case, at least on the time scale we can see here. For the red one, it's below and close, and then it's below again. So we want to investigate to understand a bit more. And in fact, if I show you a zoom at very large time, what I see is that all dashed lines corresponding to the dynamics at exceptional points, they are below the solid lines. Okay, so the crossing with the blue curve, with the solid blue curve, happens at very large time, but at the end, they are all below the solid curves. And so why is it remarkable? This I already told you. So okay, this is achieved with realistic parameters for experiments, and now we want to see, whether this really corresponds to critical damping. And so for this, we took the ratio of the trace distance at EP and at non-EP for the different initial states. And what you can see is that at intermediate times, like until time 120, more or less, one cannot say something. And indeed, at short times, no, the dynamics depends too much on the initial state. You will have contribution for different types of eigenvectors. There is no remarkable behavior. But at longer times, what you will have is that you will have always this ratio, so the trace distance at EP, which will be smaller than the trace distance at non-EP. And in the paper, we provide the proof. We derive the proof taking into account the exact dynamics of our system, and we could really show that this ratio tends to 0. And and we think that this can be like a way to assess whether your system reaches critical damping or not. So at this point, let me mention that there was a very recent paper by the group of Kate Murch that in fact Alexia mentioned also in her talk. So Kate Murch in St. Louis is working with superconducting qubits, and he is interested in this topic since several years. And so in this recent work, they still engineer gain and loss. Okay, so it's not an open quantum system, not engineered as we consider. But what is nice is that they have also evidence some kind of critical decay for a single qubit, and they mention it. And so we are now discussing with them to see how we can whether we can quantify their behavior with our measure, and if they can go to 2 qubits and see a bit the physics that we evidenced. So this is about, this workshop is about transport, and so of course critical damping via the trace distance also can be seen in transport observables. So we looked at the heat currents, and here I show you the heat current as a function of time normalized by the heat current in the steady state. Okay, so that's why all the curves are approaching 1. And you see that when the system is underdamped, then I can see oscillations in my heat current. When it's overdamped, it's the dashed line, the dotted line, so it's below. And when it's critical, there are no more oscillations, and it goes faster to the steady state. So,
sorry,
yes?
Geraldine?
Yes?
Hi, I'm Felipe. Can I ask you a question?
Yeah, of course.
Here and in the previous result about this R,
yes,
you are only projecting to the modes with 0 imaginary part, or they are included now?
Okay, so that's a good question. In fact, in the plot, no, so it's not the same. Here, I only focus on the eigenvalues with 0 imaginary part. So if you want, I compare the underdamped respect to critical, the overdamped, sorry, respect to critical regimes. But here, you see, I show you for all regimes. That's the heat current for all regimes. So this will correspond to having some imaginary contributions. That's why I see oscillations. And here it's overdamped, and here critical.
Okay, thank you.
And we, in fact, so my colleagues in Geneva, we started looking at this model because we have been working on it for several years to show that you can create entanglement from thermal resources. So we also looked at a measure for entanglement. So it tells you whether your state is entangled or not. And again, we could see that, so this is a concurrence. again, we plot the concurrence as a function of time normalized by the concurrence in the steady state. So that's why it approaches 1 also at very long times. And if you look at the inset, it's more clear. Again, in the underdamped regime, you clearly see oscillations of the concurrence. Whether in the overdamped and critical, you don't have oscillations. And the critical is the one that reaches faster the steady state value. So the critical damping that we formally derived from the Liouvillion for the reduced density operator, of course, it affects transport of observables and quantum information measures that may be of interest for achieving different tasks. And so this brings me to my conclusions. So I think what is nice is that we could demonstrate the existence of exceptional points in an open quantum systems where you do not necessarily tune gain and loss, okay? And we could evidence critical damping at EP, and in an open quantum systems, to our knowledge, this was not done before. And this corresponds, it's in exact analogy with the damped harmonic oscillator. And so now you see, for the future, I think this can open or this can lead to new ideas, no? Because here, if you want, it's a type of quantum control, but it's not with any work input. It's not that we send electromagnetic fields to control dissipation and so on. It's by choosing a certain point in parameters, in the parameter space, that you can control how your system is evolving towards a steady state. And so it may have advantages, for instance, for operating quantum Sommel machines, no? Which, because in many works, we are interested in steady state quantum Sommel machine. And as theorists, we always assume, okay, we are in the steady state. But one could ask, okay, how much time do you really need to reach the steady state? And maybe you see where if you take into account this to compute the efficiency by operating at an exceptional point, it can constitute an advantage. And on a fundamental side, I think it's there are many open questions. For those who are a bit familiar with this research direction here, so we looked at exceptional points in the Liouvillion, so looking at the full quantum dynamics. But one can ask, okay, what happens if I neglect the quantum jumps in my dynamics? Then you may know that your Lindblad master equation can just be can take the form of a unitary evolution where your Hamiltonian is some effective Hamiltonian, which is non-Hermitian anymore. And so with that, we want to investigate, for instance, the role of quantum jumps by looking also at these types of signatures. And well, there are many more open questions, but I close here, and I thank you very much for your attention, and I'm happy to take questions. Thank you very much.
Thank you, Geraldine. Thank you for the very interesting talk. Are there questions? Carlos has one.
Yes, hi. Thanks for the nice talk. So exceptional points have a long history, right? So it's yes, from random matrix theory, and then it's been observed in bosonic systems and in Bose condensates, and now they are, exploding, even going to classical systems. And one of the things they usually mark or they are associated with are dynamical.
Sorry, your connection is, I think, not so good. Is it mine or?
No, I think it's Carlos' connection. Carlos, can you repeat the last
sentence?
Yes, sure. No, I was saying that in essence, exceptional points are usually connected to dynamical phase transitions, or
yes,
non-equilibrium phase transitions. Here we don't see that, I guess, because the system is too small. But I would say that one would expect to see more exceptional points when you consider, a larger amount of qubits, or a slightly larger.
No, of course, you're completely right, and for us, yes, for me, it's really an open question. If you start wondering about these dynamical phase transitions, typically they were investigated in PT symmetric systems. And in fact, this 2-qubit model is, in general, it's not PT symmetric. So we have an exceptional point, but without PT symmetry. So with my students, we are determining the conditions under which this system could be PT symmetric. And I agree, but I don't know for the moment if we can evidence a dynamical phase transition. It's not clear for me. But as you say, I think if we go to larger systems, okay, it might be a good option. And what, to my opinion, could also be interesting is that you have different orders for EP, no? Because, and the larger your system is, the larger chance you will have to have a high order exceptional points. And so one question is are there different signatures for different orders of EP? And I think this in classical systems, it has also not yet be really understood, because apparently maybe you know that better, but in classical systems, I did not find works mentioning high orders exceptional points. Two second order EP, okay, of course there were evidence, but even third order, in fact now, okay, I have a doubt, but here, for instance, in this very simple model, also it's small, we could evidence a fourth order EP. So I think by looking at quantum systems, we can go to higher order EP. But okay.
I would expect some, I don't know, some years ago or many years ago, there was a connection between quantum phase transitions and some sort of transitions observed in the concurrence in the entanglement content. So maybe in systems like that, which is usually spin systems, exceptional points will appear and will mark these transitions somehow.
Yeah.
It's interesting. Anyways, thank you.
Thank you.
Any more questions?
Yeah, I have a question. You mentioned that at the EP point, your relaxation is the fastest. Is there some proof that you can say the opposite? Given that your relaxation is the fastest, you have EP point?
So no, no, because in fact, you see, when I can show you that very okay. No, because if you are in the underdamped regime, in fact, you may be, and you can see that on this plot, even if it's for the heat current, you may be closer to the steady state before the critical regime. So really, critical damping, it's not only to reach the steady state in the fastest way, it's the fastest way when you have no oscillations, okay? So that's really the transition between oscillatory and non-oscillatory behavior. And among the non-oscillatory behavior, it's the fastest.
Okay.
So it's no, because I could always provide you with some values where you will be in the underdamped regime, so with oscillations, and you could be at a certain time closer to your steady state than in the critical regime.
Thank you.
You're welcome.
Questions?
So I have another question if no one wants to ask.
Yeah, go ahead.
So you worked a lot with the third order, and in your reply to Carlos, you also mentioned a little bit on the kind of classification, if it's a third order or fourth order. But what I saw from your talk is that because you have a third order, you have this in your one of your matrices, you add this time to the power 2. That's right? That is related. So that is the signature of the third order, and if you would had a higher order, it would be t to the, the
t to the third. Yes.
Yeah. Okay.
Yeah, exactly. Because this then it's really related to Jordan form. So indeed, if you have a higher degeneracy, you see you will have a bigger upper triangle to fill in with your Jordan with the coefficients, but as I said, no, this, so, okay, indeed, no, it was a bit misleading. You can have signatures of different types of orders of EP, but the difference between the t squared or the t to the power 3 or t to the power 4, in fact, I don't believe this can be evidenced experimentally. So, in fact, I was more interested in determining whether there are different types of signatures on the dynamics, like critical damping, but maybe it's in by looking at phase transitions, whether there can be easier signatures for different orders.
Okay, thank you.
You're welcome. I saw that there was some questions in the chat also.
No, there's Gonzalo who raised his hand.
Okay.
Hi, Geraldine. Thank you very much for the talk.
Thank you.
I want to ask just something that wasn't very clear for me, is about the initial states. So you say that you need to activate all the modes, no, or something like that. So do you have any idea or what initial states, starting from which initial states you will not see this critical?
Okay. So it's a good question, and in fact this is why if you take a random initial state, you will see this critical damping. Okay, here I took 3 examples of initial states: the singlet, the ground, and thermal, because these are like initial states which are relatively, I think, easy to achieve experimentally. But let me say that the states, so you will see critical damping with all the states. But what happens is that if I look at the short time signatures, in fact, if I take a random initial state, I won't see this polynomial dependence in time, because you see the exponential here, the negative real part are larger than the one in the lower part of the matrix. So in fact, the exponential decay will hinder the time polynomial dependence. So if you want to evidence this time polynomial dependence, you have to choose an initial state which is probing exactly this region. You see these eigenvectors. But this is like a mathematical construction because we knew the exact solution. But I can tell you that the set of states corresponding to probing exactly this sector is a set of measure 0. Okay, it's it's nothing. It's completely artificial. Okay, and for the signature of critical damping, it does not depend on the initial state. Of course, the exact dynamics will depend on the initial state, but for all of them, you will see critical damping.
I have a question myself. There are a couple of minutes. Well, it's sort of nerdy questions. I would probably ask you during coffee break, but I'm not sure I can ask it anytime soon. So I ask it here. So you consider the case where the largest eigenvalue, or the eigenvalue with the largest real part is 0 in your Liouvillion or Lambertian.
Yes.
And in the classical master equation for ergodic stochastic matrices, we know that, well, depending on whether the time is continuous, discrete. Anyway, we know that the largest eigenvalue is actually 0 and is non-degenerate in the case of continuous time. And you have this theorem, the Perron-Frobenius theorem, that ensures this this result. Do you know if there is anything similar in the case of the quantum Liouvillion or Lambertian? So how should it be or look like, or which are the properties for the largest eigenvalue, or the eigenvalue with the largest real part to be 0? So for the system to reach a steady state, which is unique.
Okay, so is it correct that your question is about the general condition under which you can prove the existence and unicity of the steady state?
Yes, yes.
Okay, it's not. I think it's not direct. No, it depends on the form of your dissipators. It depends whether the spectrum of your system is degenerate or not. So I know there are ways to, given the spectrum of your system, you can see whether there is like a single criteria to determine that. I don't know. I think it's a complex question in general. Okay. So in the talks we heard in some recent works, people are looking at what is called the strong symmetry, where they have some simple arguments, this to know whether there are degeneracy of the steady state, but to so that's something that it exists, but to have like the same type of criteria to determine whether it's unique, this I'm not sure it exists.
Okay, maybe I will ask you in private if you can point me to some reference.
Yes, yeah. With a colleague of mine, it's a mathematical physicist in Grenoble. We were considering a tripartite system, so ABC, and we were demonstrating the existence and unicity of a steady state. But this, again, okay, it was quite general, but still we determined it was a tripartite system.
Yeah.
There is one question in the chat by Sanjana Pat. Can you please once again explain? Yeah, because it was a direct message, sorry. So can you please once again explain critical damping at exceptional points? Does it directly, indirectly affect the long, short type signatures? So I think I gave some already some answers to that questions. If you're in the short time, you cannot see critical damping. No, critical damping is in the long time, because it's how it approaches the steady state, and in the short time, depending on your initial state, it's very random. So it's more in the long time that you can really prove this behavior. And critical damping at exceptional points, it's really so the limit between oscillatory and non-oscillatory behavior. And among the non-oscillatory behaviors, that's where you reach the steady state the fastest way. So I hope I answered your questions.
So there's Ellie who raised his hands, and then Carlos, you're writing something.
Yes, there was also another question. I also got it from Surender Pratap. Determinant of L is coming equal to 0. Suppose it is non-zero, will it affect your results physically speaking? why would my determinant, the determinant of the Liouvillion be 0? Well, it's too, so okay, of course, if it's diagonalizable, but then if it's not 0, so it's, okay, correct me if I'm wrong, but so if it's not 0, it's non-diagonalizable. And then if it's not diagonalizable, anyway, you cannot really play with EP, no, because EP, that's a mathematical game that you play with the spectrum of your Liouvillion. So I think it does not apply to that case. But I may miss, okay, there might be some subtleties that I miss, but I think it's not, you should have initially some diagonalizable Liouvillion.
Okay, last one from Ellie, and yeah.
Yeah, I have a very technical question. I mean, if you have a degeneracy in the ground state, so you have many lambdas equal 0, so is this can be also considered an exceptional point, or is this excluded?
Wait, good question. So this is the case where, no, okay, so if you have, so you remember the, okay, the spectrum I showed, no, in the complex plane. So I think your question relates when you have so multiple steady states, so meaning that one of them has real and imaginary part equal to 0, and the other ones have some imaginary part which is non-zero, no?
No, that all of them have 0.
Ah, all of them are 0.
So then the eigenvalues are the same, but I don't know.
No, so it's not, because an EP is defined as like the merging of eigenvalues. So this will be okay with what you say, but also the coalescence of the eigenvectors. And if the steady states are different, it means that, well, these are the eigenvectors corresponding to the degenerate eigenvalues, but so it means it's not an EP.
Right, okay, thank you.
You're welcome.
Okay, I think we can stop here. We're already over time, but yeah, thank you for the very interesting talk and discussion. Yeah, let's thank.
Thank you very much to all of you and for your questions.
And thank everyone for attending today, and hopefully see you next week.
Yes.
We start again on Monday.